Hello, everybody, and welcome to the Trusted CI webinar for January 27th, 2025. I'm your host, Jeanette Dopp-Heidi. Trusted CI is the NSF Cybersecurity Center of Excellence, and these webinars are part of its mission to deliver high-quality, actionable guidance regarding cybersecurity to the NSF community. More information about Trusted CI can be found at trustedci.org. Today's topic is a unified monitoring approach to enhancing the security and resiliency of hazard workflows. Our presenters are Sudarshan Kanan, who is an assistant professor at the Computer Science Department at Rutgers, and Ram Durerajan, an associate professor of the School of Computer and Data Sciences and co-directs the Oregon Networking Research Group, ONRG, at the University of Oregon. Welcome, both of you. Before we begin, I have a few things to note. First, this is being recorded. Second, attendees are welcome to ask questions during the presentation. You can use the chat box, and I'll be monitoring that during the presentation. And with that, I will hand things over to Sudarshan. Sudarshan, welcome.
Thanks a lot, Janet. Welcome, everyone. Thanks for attending the talk. My name is Sudarshan Kanan. I'm an assistant professor at Rutgers, and I'm going to present our work with my collaborator Ram Rajan on some of the interesting developments that we have made on this project. So this talk is about unified monitoring approach for enhancing security and resiliency for hazard workloads. So to kind of set you some context, as we all know and have been hearing in news, the naturally occurring geohazards are some of the biggest threats that we are currently facing as community. And they have a huge societal impact, specifically with their increasing frequency. For example, in 2022, the cost of 18 hazards was around like $165 billion. And if you talk about 2024, 2025 with LA fire and so on, these costs are going to more significantly and substantially increase. Beyond these, they also have huge impact on the overall infrastructure. For example, computing infrastructure, such as say network infrastructure, that results in significant loss in connectivity. So as a community, as cyber infrastructure community, building resilient CI and like workflows that support and monitor these geohazards, there is an urgent societal problem, and that's kind of the focus of our kind of like the problem. So one thing that kind of led us to this is through kind of interaction with kind of different kind of groups that work on the hazard monitoring, and is that they have been like deploying like more cross-boundary heterogeneous approach to monitoring these systems. For example, there are kind of computing elements near the actual kind of site where these hazards could potentially occur, such as kind of having edge nodes and a lot of sensors. They use wide area network to kind of either talk with some of the local cloud, or they talk with HPC data centers and so on, and the data gets kind of eventually gets processed. The cross boundary approach is great because it now kind of has this interaction across different types of system in a more collaborative approach. But this also kind of introduces new potential for threats in a more cross boundary approach. For example, some of them could be just end-to-end resiliency, given that there are like a lot of kind of wimpy computing elements combined with large-scale data centers connected through wide area network and so on. For example, if you end up losing like a few kind of like local edge nodes, this could kind of result in kind of like loss in kind of like accuracy of how you predict these things. For example, failures in sensors, as we kind of discussed with some of our collaborators, are very frequent. Beyond just the physical kind of like resiliency, there is also kind of like security related challenges with the cyber infrastructure. One of our discussions with like, for example, the SAGE team at ANL kind of helped us to kind of understand that right now some of these systems are to some extent kind of built with like more simpler hardware, where the focus is to kind of get job done, and which means is are also kind of prone to some of the cyber attacks and so on. And for example, one of the examples that we're going to also kind of present today is kind of like targeted link flood attacks on network links, and that can also have result in DDoS attacks on these wildfire workflows. So with this stage, what is our kind of approach? Our project is about hazard mon. Our goal is to kind of have this three-pronged approach to kind of addressing this problem. First thing is that we want to first kind of develop this end-to-end monitoring infrastructure that can kind of monitor resources across the edge, across the cloud, across the network, and so on, and get more accurate and more kind of detailed understanding of what's happening out there. Second, we want to kind of provide this infrastructure to very quickly kind of like either process some of these kind of like telemetry locally in each of these computing nodes, or kind of disseminate to kind of like more like HPC clusters or data centers to kind of have a more kind of like a more kind of detailed understanding of these stuffs. And the last thing is essentially like, how do you, now that we have collected these kind of like metrics, how do you kind of like avoid both kind of like overcome physical threats as well as cyber infrastructure threats? So when we started this project, we wanted to study a multiple kind of like hazards. Right now, we kind of started with this kind of like a very specific use case of wildfire, which kind of has because of like more prevalence of data and so on. And we kind of like started understanding that these hazard detection systems require extremely high accuracy and performance. For example, I'm kind of showing you three images at time 0, time 1, and time 2 taken from like a real kind of hazard workflow. For example, at time 1, you can see that all the green boxes here kind of show kind of like an actual wildfire. But if you kind of use any of these current systems with low accuracy, at time 2, you could see also that there are some kind of false positives that could be detected. The point here is not about just these specific images, but more specifically, identifying some of these hazards is challenging than it seems, and this could lead to increased delay hazard detection and potential loss of life. We studied a lot of potential state-of-the-art systems, and to some extent that we have collected data from, they take somewhere between like 20 to 50 minutes for more accurate kind of detection, and that's quite significant amount of time even for a classroom size fires. So what are the immediate challenges on these systems? First, so through our collaboration with kind of like ANL, we have been studying the SAGE system, and we wanted to first understand more accurately map out the infrastructure of these systems. First thing is that, for example, here you can see some of the SAGE sensor nodes that kind of monitor these kind of wildfires. These are kind of like these are kind of nodes with reasonable amount of processing power. These are, I'm going to refer them as edge nodes. They typically run kind of like a combination of machine learning and image recognition algorithms. They use high performance components like GPUs and like storage and memory and so on. And they are or then kind of they interact with kind of a local cloud or kind of like local like data centers. There's a kind of a micro data center, which I'm going to kind of refer to as, which is also used where people use this terminology called HUT, that has like more kind of like capability to process data more locally before the data is kind of sent to a remote cloud for cloud training and inference or HPC data center. So the first thing that we realized was that on this big cross-boundary solution, there is a lack of end-to-end unified monitoring framework to capture and kind of resource usage across all these kind of different computing spectrum. And we also found out that when the network capabilities are kind of poor, because remember, these are all connected through wide area network and so on, we kind of understood that disseminating some of this telemetry over this unreliable network can have kind of huge challenges. And the last thing is that there is even lack of solution to kind of identify, categorize, and mitigate some of these kind of threats, because and all of these kind of contribute to kind of overall detection of wildfires and so on. So we started with the first goal of let's go and build this end-to-end monitoring, which we call as Hazard Mon. The basic idea is to kind of like build a monitoring capability across all of these spectrums, where different kind of like we have kind of monitoring capability for sensors, we have monitoring capability for some of the drivers, for GPUs, for CPUs, and so on. And we are kind of trying to tie up with some of the monitoring capabilities that are kind of present for like the cloud and so on. So we have kind of developed a reasonable monitoring framework. I'm going to discuss about the infrastructure and so on that we have been developing. We've been able to kind of like develop a decently kind of like kind of an evolving monitoring capability that kind of logically kind of unifies an end-to-end computing resource monitoring infrastructure spread across different nodes. This has been kind of the contributions from like a couple of PhD students, both at like Rutgers and like UO, and a combination of undergrad students who are actively contributing to this project. So for the driver application, Our goal is to kind of like we use this framework called kind of like YOLO, which is kind of combination of OpenCV and machine learning framework, which kind of like known to have like higher precision and so on. But one of the challenge is that specifically running some of these inference on like low power kind of edge nodes, we have observed that there is a huge trade-off of in terms of higher precision and energy efficiency. So we kind of like not only these undergrad students are not only kind of like developing monitoring infrastructure, but they are also looking at like when there is energy efficiency problem, given that some of these ML frameworks are extremely energy expensive, what can we do to kind of like combine with some of the more simpler kind of algorithms, right? So in the year one, we kind of like partially implemented and evaluated a simple detection algorithms on low power platforms. For example, on Raspberry Pi, Jets and Nano, that has kind of actually some of them replicate the Sage infrastructure. And we try to kind of understand the trade-offs between resource usage and so on. Now, with respect to the infrastructure, and this project, because it demands like more like having a more cross-boundary kind of infrastructure. First, with respect to kind of both data center and kind of like micro data centers or local kind of like edge, we kind of using a combination of kind of two folds. One, through collaboration with kind of the Sage team, we have access to the Sage nodes that are kind of some of the actual nodes that are deployed in Wildfire data center. Fortunately, Rutgers also has a micro data center. You're seeing an image of a micro data center, which was an NSF kind of sponsored infrastructure called Parasol that has kind of accurate kind of power limits and so on. It kind of replicates a hut in a Sage infrastructure that could be present in some of the wider area. They're solar powered. They have capabilities for connecting through kind of like through kind of regular grid, but we can also kind of now, and it has like more accurate power measurement on how much can we do inference and what can we do to kind of like drive some of the requirements that we have. Beyond that, so this is kind of like more the micro data center infrastructure that we have developed, but we have also kind of developed more kind of the edge because we want to do accurate kind of performance as well as power monitoring. We have been able to kind of replicate some of the Sage nodes using like a combination of Raspberry Pi and Jets and GPUs, connect them to the power source and understand how much is kind of the power and performance trade-off. So based on these infrastructure, our first work was to kind of say, okay, let's have this basic hazard mon and kind of identify what are the potential pitfalls when we are running these complex applications that are kind of doing wildfire hazard detection. This work was kind of like presented late 2024 at the hot topics at hot infrastructure workshop. And I'm going to kind of present some of the brief findings that we kind of like got from our initial work. So as I said, the Sage infra, we kind of like replicating the Sage infrastructure as a kind of a good model. So here is an example of a sensor node that has an edge device that's kind of running this framework called YOLO, which just says you only look once, kind of an algorithm that does inference of the wildfire. They are connected to a micro data center or micro cloud, which is generally called hut. And then they kind of talk to the actual edge node. So one thing that we observed as a first thing is that some of these micro data centers and edge nodes to some extent replicate the same set of applications that one would actually use in the regular data centers, except that their properties are slightly different. For example, if you look at like the micro data center cloud, they run a combination of training containers. What these training containers do, they basically kind of collect all the images from the actual deployed edge nodes, continuously train on them, and then kind of deploy the models for inference across the edge. They also use database containers, which means that they continuously collect images and store these database images from different kind of sensors, not only kind of wildfire kind of sensors, but also like, for example, bird watching and weather and so on, and also kind of things like Redis container and so on. And they are truly heterogeneous, which means that they are kind of running a combination of CPUs, GPUs, and so on. The most important challenge is that we cannot take some of the solutions in the actual cloud and kind of like try to replicate here because let's say, for example, if you're running different kind of containers and different workloads in some of these micro data centers that's deployed in the wild, you cannot simply scale this across like multiple machines or multiple virtual machines that you could do in a traditional data center because of the resource limitation and the energy limitation. So one of the problems that we kind of like found using our kind of like initial hazard mon framework that kind of identified this is that most of these generally kind of like this edge micro data centers that support some of these kind of deployed sensors is that they're generally oversubscribed. they are multi-tenant, which means they can run a combination of different kind of applications, and plus added with strict power limitations. So, which means this requires kind of like a more kind of like trying to kind of have more energy and kind of resource efficiency balance. Oh, 1 minute. Yeah. So what are we monitoring in these infrastructure? We are monitoring for limited computing resource, like for example, forced multi-tenancy oversubscription challenge. We are also monitoring for energy limitations, the point at which you have to kind of hit like beyond 10 kilowatts per hour. That's kind of our initial default model. We're also kind of monitoring for deploy location challenges. What happens when these are deployed remotely by varying different bandwidths and network conditions and so on. Uh, we are also monitoring what happens when there are interaction between different types of applications at the same time. How does it impact not only like just the application, but the overall cyber infrastructure and things like resource contention and so on. So we kind of like based on our initial deployment, we kind of first found out that uh, uh, the first kind of biggest bottleneck across these kind of like system was beyond just the compute capability, the memory resources in these kind of like edge nodes are kind of like quite restricted. And because these applications, some of them could be compute and memory intensive, some of these applications like databases and key value stores can be memory intensive. It seems like in these kind of edge nodes, against standard principle, memory seems to be kind of one of the biggest kind of like bottlenecks in this. And we try to kind of take each of the different data center solutions and see if some of them can be applied. And we found that under strict energy and power requirement, it's very hard to kind of directly take some of the energy, some of the techniques that has been used in traditional data centers and apply in this context. So to kind of give you some kind of like magnify into this resource contention problem, we specifically took kind of like two applications. One is the YOLO, which is continuously training on like all the wildfire images, and a database application that continuously is kind of storing all the images that obtains from different kind of like from the Sage kind of like sensor nodes, and it's continuously kind of trying to store the data, right? And one thing that we found was that both these applications run on their own container, but they have significantly different kind of like energy consumption and resource consumption. So uh, here is a very simple hardware combination in the configuration. In the interest of time, I'm not going to kind of like go in detail. So this kind of replicates some of the micro data centers that shared infrastructure have. For the wildfire application, we're running like the ML training wildfire detection application. And for the database, we're running a no SQL key value store. Uh, so for the analysis, first thing that we observed was here is kind of the two applications. The first application is the database, and the second application is the actual like image recognition algorithm. The y-axis for the database shows the throughput, and the y-axis for the YOLO application says the time to actually detect some of these kind of like wildfire. As you could see, one of the thing that you can observe is that when the memory is quite significantly high, for example, at 48 GB, both these applications, either they are running isolated or when they are running in a shared manner, things don't get impacted. But as can you kind of keep reducing the available memory for some of these applications when the contention becomes quite high, you could see that there is a huge impact when you're kind of running these applications in a shared infrastructure. For example, the database application that is extremely critical for collecting all the images from different sensor nodes and kind of trying to disseminate this data over network has a more drastic performance reduction compared to a training application that runs continuously on these nodes and then kind of trains on the image to kind of deploy this model. So the point here is not to kind of say, okay, these are the only two choices of application, but the point here is to say that in these nodes, multi-tenancy is a significant problem given the different types of applications they are supporting. And there are not too many options to simply just scale. So which means we need to kind of develop new techniques to kind of see how to kind of efficiently schedule them. So, so here is a kind of like, so this is a very simple example of what could be happening in these kind of like systems. So what is our current system doing? Based on the kind of insights that we kind of gained from Hazard Mons, kind of like monitoring framework, I discussed only the memory problem, but we are kind of developing more kind of like a more dynamic and more kind of like configurable application and runtime level selector to design different important metrics that's kind of important for each application. For example, a bird watching application might have a completely different requirement compared to a wildfire monitoring application. We're doing this end-to-end kind of like monitoring and kind of like configuration selection approach that can kind of try to identify using a combination of machine learning and systems technique to kind of see what's the best way to kind of like do resource allocation and select the best configuration in ways that doesn't impact different applications. And the configuration selector's most important goal is to optimize across different applications, but also consider different trigger events. For example, when there is no wildfire, when things are all fine, the configurations could look completely different. But when there is a trigger, for example, there is actual wildfire happening, the way we kind of configure these applications and the way we kind of configure resources across these systems is going to be completely different. And some of these context specific information is extremely critical, and that's kind of our focus. Our second goal is to kind of enhance security posture. I'll now kind of like allow my collaborator Ram to kind of start discussing some of the progress that we have made. Over to you, Ram.
Great. Thank you, Sudarshan. I'm going to quickly share my screen. All right. So the second, complementary problem to what Sudarshan was talking about is the security problem and how, this cross-boundary approach to enhancing resiliency for, these hazard workflows faces every day. And specifically, I'm going to talk about a key problem that many stakeholders in the internet face, which is the distributed denial of service attacks. And then I'm going to focus on the edge networks that kind of play a critical role in terms of moving traffic all the way from the sensors via the wide area network to the cloud and HPC backbones. And these edge networks are often the key place where DDoS attacks happen. And so let me just zoom into a specific aspect of edge network. So think of this to be an edge network where you have a border switch that sees traffic from pretty much many parts of the internet. So you have the external IP addresses. Most of them they send benign traffic, and then they go to the border switch where some sort of basic checks happen, and then they go inside the perimeter where, for example, your HPC servers there are, some sort of a protected servers there to, come up with any sort of wildfire detection in our context, right? So given this, there is also, of course, in addition to the benign set of sources, there are also attackers who are constantly trying to, either attack your border link or some of the access link towards your protected server, such that the benign traffic, especially your workflow, could be affected. And then the key property with any of these attackers is that they just don't start with some sort of static addresses. Maybe they do, but then they constantly change, and the attack sources change all the time, which means that your edge network, one, has to be accurate in terms of detecting the attacks. The resource that you use on the edge network, for example, the border switch that you might employ to detect these attacks, has to be completely scalable. And three, in the face of all these changing attack sources, you have to be robust enough to capture all sorts of attack signatures so that your hazard workflow can be effectively protected. So typically, what we use for a case like this is a DDoS signature detection technique. Given that our focus is on link flood attacks, we're going to be focusing on the volumetric DDoS signature detection problem, where the traffic is monitored by a programmable switch from different sources, and then this is all sitting in the data plane where you see the traffic at line rate, and then it goes to a control plane where some sort of decision making algorithm, logic, machine learning, statistical technique, whatever, runs, and then they decide whether an attack is coming from a particular source or if it is benign traffic. And then based on the decision, you employ, again in the data plane, some sort of a mitigation strategy. Let's say drop the attack sources, or rate limit the traffic, or collaborate with an upstream scrubber or a provider such that you take some of the suspicious traffic and go scrub it and then come back. Right? So you do all these decisions at line rate with your typical programmable switch. And if you think about, many of the state-of-the-art technique, we, studied a bunch of them, one being a sketch, which implies some sort of a probabilistic data structure. So they have hash functions, and if you send all your, traffic, signatures via them, they come up with, some sort of a way to map them to say, all right, if it crosses a particular threshold, it is essentially a DDoS, or if it doesn't, then essentially it is benign traffic. So you monitor them and then, send it to the control plane where you say, all right, employ these, and then you figure out whether an attack is happening or not. But the key thing with sketches are that they're going to have so many false positives, right? Sometimes your, benign traffic is affected so much, and we studied a bunch of sketches, and, two examples here. We looked at Euclid. Another one is, recent state-of-the-art JCON, where we see about anywhere between 4 to 50% positive rate, false positive rate for realistic attack scenarios. And we emulated about 50K attack sources in our experiments. And this number is actually jarring. So we cannot just like that deploy any of these sketch-based techniques, which kind of is at odds with our first requirement of this attack signature detection has to be accurate, and sketches are not. And then we also studied another class of techniques based on machine learning, where if you have individual addresses, you create address-specific features using your monitoring capabilities, send them to a trained machine learning model, and then the model will decide, all right, here is an attack, or here is a benign source, and then based off of that, you go do the appropriate mitigation. But then the key challenge with deploying any machine learning solution is, one, it's all on the control plane, which means that if your traffic is coming at the rate of 10 to 9 packets per second, you can only act at the rate of 10 to 5 packets per second. So you're already losing a lot of packets when you do the detection. So there's going to be overheads. And then the way you implement some of these algorithms, you cannot go deploy them on your switches. So which means that you have to compute all these features on the switches and then translate that to the control plane. And so if you think about a technique like Lucid that has done machine learning for DDoS detection, they would require anywhere between 80 to 90 megabits of switch hardware memory, which is very costly. And so if you just add that in terms of the number of IP addresses that you're currently monitoring, it's going to quickly exhaust all the the sources that you have at the switch, which means that the machine learning techniques has to be a bit more principled enough and not work at the granularity of individual addresses, but then maybe you have to look at a more aggregated fashion to detect these attacks so that you can overcome these overheads. And then there is also the third class of technique called the prefix level defenses. So one of them is Dream. So that's a technique that instead of looking at individual addresses and coming up with features, they aggregate them and then look at them in the form of prefixes. But then they again have a whole bunch of issues because they are pretty much based on counters and thresholds, which means that they are not dynamic enough to zoom in all the way to attack sources, and then they give up easily. And so we see a number of false negatives with them as well. So we have to think about techniques such that you satisfy accurate DDoS detection, but at the same time be scalable with increasing volumes of traffic while being robust against changing attack sources. And all three classes of techniques that we found to be working on one of the dimensions that we want to solve, but not all three dimensions. Hence, we created what is known as Zapdos, which is a prefix level machine learning approach, which dynamically refines attack sources. So we start with the prior prefix level defenses. So we also consider prefix level defenses, but then we apply machine learning to opportunistically separate prefixes where there are attack sources, and then we create algorithmic components to hold out some of the benign sources where hazard workflows might be sending traffic. So our prefix level technique can actually see through some of the ambiguous prefixes. And this was not easy, so we had to do simulations for about 100K attacks, and we did not have the data set, so we have to take our own data fusion approach to create the data set first, to create the machine learning model to solve this accuracy problem. And then the key idea there is we leverage this mathematical property called multifractals. So the idea is, if you take any of the attack sources or the benign sources we have, they're always clustered, and they exhibit this sparsity when you think about longer prefix lengths. So for example, we took the Mirai attack sources and studied about 50K attack sources in them, as well as 5 million Mavi attack sources. And we found that if there are attack sources that are at a higher prefix length, essentially, as you zoom in, they are clustered and you still find those attack sources. So we exploit this property and train your machine learning model to catch these. But at the same time, we also come up with this algorithmic component, as I mentioned. One example is a look-ahead technique where we only monitor all the non-empty sources that contain some form of an attack in our technique. That's going to take care of scalability issues. So for example, if there are benign sources, we don't even consider them in the subsequent rounds when we monitor them. And so here's a quick graph that shows how Zapdos, when we employ the prefix level machine learning algorithm with the look-ahead technique, can actually refine and accurately predict. As you can see on y-axis, we show the false positive rate as well as the false negative rate, and much better than the state of the art for both the solutions. And within about 100 seconds, we can actually generate accurate attack sources in a scalable fashion, whereas some of the state of the art, they struggle so hard with high false positive rate and high false negative rate. And then the key problem still with Zapdos is that, okay, we zoom in with look ahead and we know that there are all these attack sources. But then if you recall, I also said attackers change sources all the time, which means that, for example, if you consider something at time t, maybe there is a new attack source that has started an attack, and the attacker has been evolving in terms of how they are attacking the edge network. So we have another technique called look back, which employs a simple Bloom filter at the higher level prefix length. And then if there is some sort of a change, it is detected immediately in the next time window. And then based off of that, in the subsequent rounds, that new detected source level information is actually zoomed in, and that focuses on what has changed and what has not changed in the subsequent iterations, and that takes care of the robustness requirement that we set forth. And so we have simulated this for about 100K attacks, and we tried faster attacks where the attacker is constantly changing addresses in a really rapid fashion, medium pace, slow pace, and across all of them, we had really low false positive for Zapdos, as well as the false negative rate. They converge quickly in about 100 seconds. So this again tries to demonstrate that Zapdos can effectively address all three requirements that we set forth. And this is not just about simulations. We actually implemented this with real Tofino prototype, deployed this at the border of UFO campus, where there is a lot of wildfire workflows coming in, as well as all the earthquake shake alert stuff coming in. And we showed that we can do a whole bunch of implementation optimizations. So one of them is packet ferries, which is a new technique that we have introduced to collect the telemetry quickly to come up with attack signatures on the fly. And then we have evaluated this for over 100 attack sources. Again, all the details are in our Oakland paper, which appeared earlier in 2024, and that shows the promise of this technique for a whole bunch of volumetric attack scenarios, and which is over 100 attack scenarios, and we showed that this works for attacks where attackers spoof their attack sources as well. In addition, if the upstream border link is flooded, even in those scenarios, we showed that Zapdos can effectively mitigate the impact of volumetric DDoS attacks. And this is just one part of the problem, right? I mean, DDoS is one aspect of the problem that we are focusing, but then if you think about this architecture that we have, which is composed of sensors, edges, all the way to the HPC centers, there are several security threats, and currently our focus is on enhancing the telemetry capability that we have and combining some of the telemetry capability that we have on the networking side with what Sudarshan and some of his team members are developing on different aspects of the end systems, and then combine that together to form a unified way to enhance the security posture of this end-to-end approach. And we expect a number of security features that involves monitoring on the edge, wide area network, as well as HPC. And so to conclude, I mean, there is this very clear need for fine-grained monitoring that can enhance both the physical and the cybersecurity posture of the hazard workflows and hazard CI. And as we showed, I mean, multi-tenancy is a key problem here, which opens up a lot of issues in such a resource-constrained environment. And there is also a need for predictive models that we could use for DDoS detection and performance improvement and all that. We just presented two preliminary efforts here. One on volumetric attack and one on performance enhancements in the face of multi-tenancy. But then in the ongoing effort, we are working on a number of enhancements that we can bring from some of the end-to-end monitoring capabilities that we have built to address many of the security problems that we have in this space. With this, we're happy to conclude and would be happy to take more questions. Thank you for having us here.
Thanks. Let me grab the screen back real quick, and I will let people type questions if they have them. But I wanted to make just a couple of announcements. First, our next webinar is Monday, February 24th at 10 a.m. Central. The topic is Trusted Resource Allocation in Volunteer Edge Cloud Computing, computing workflows, pardon. And our speaker is Prasad Kalyam. For those experienced webinar attendees, Prasad presented a few years ago, so he will be returning back to the Trusted CI webinar series. Let's see. I will give one last call for questions, but for those of you watching, if you want to know more about Trusted CI or our webinars, you can view presentations, join the announcements mailing list, submit requests to present, all of that at trustedci.org/webinar, or email us at webinars@trustedci.org. Any final thoughts from you, Ram or Sudarshan?
Not much. I think we are making some progress, and probably some of the things that we are currently in progress, I think we'll have like even more updates probably next year or so.
Great. Okay, well, I want to thank you again for presenting, and those of you who are in attendance. I will be cutting a video file of this and uploading it to YouTube probably later today. So if you want to share, please do. And with that, thanks everybody for attending, and see you next month.